All right, let's get to it. So starting with number 2, it says you're dealt one card from a 52-card deck. Find the probability that you are not dealt a 3. Okay, so in other words, you're looking for the probability of not 3. Now, of course, there's a couple ways that you can do this, but the way that was sort of stressed in the lesson is that if you're looking for the keyword not, then that just means you're doing 1 minus the probability that you do get a 3. So the probability of getting a 3, well, how many 3s are in the deck? 4 out of 52. And so remember the shortcut was to take 4 from 52, or if you want to reduce it first, that's fine too. Let's go ahead and reduce it. This is 1 minus 1 over 13. Okay, so taking 1 away from the denominator, you get 12 over 13. I reduced the fraction first. So 4 goes into 52 13 times. And then our shortcut that we learned last time was if you're just subtracting from 1, then this is just going to be a 13 over 13. So the shortcut is take the numerator away from the denominator, and that gives you the new numerator. Okay. All right, number 25, a single die is rolled. Assuming it's a 6-sided die. And so you're looking for the probability of an even number or a number less than 5. So what's the key word in this problem? Or. And so when you have an or problem, you have to ask yourself, is it possible for you to get an even number and a number less than 5 at the same time? Yes. Okay, so because it's possible, well, first of all, or says that you are adding these two probabilities together. So the probability of getting an even plus the probability of less than 5. But since you can get these two at the same time, you're also subtracting the probability that you get both. Okay, so the probability of getting an even number. How many numbers on the die are even? 3 out of 6. Okay, the probability of getting less than 5? 4 out of 6. And then how many are both? 2 of them. Right? So the 2 and the 4 are both even and less than 5. So 2 out of 6. Now this, in the last problem we reduced, but in this one it would be helpful not to reduce until you have added your fractions together because you need a common denominator. Okay, so 3 plus 4 is 7, and 7 minus 2 is 5, so you get 5 over 6. Okay, for 33 you have a spinner. And you're looking for the probability of an even number or a number greater than 5. Okay, key word in this problem, or. So that means we are adding our probabilities together, the probability of even plus the probability of greater than 5. Is it possible to get an even number and a number greater than 5 at the same time? Yes, okay, there are even numbers greater than 5. So we're going to subtract the probability of both. Okay, so the probability that you would get an even number, 4 out of 8. Okay, the probability of a number greater than 5, what was that? 3 out of 8. And the probability that you have both, 2 out of 8. Any questions on where those numbers come from? Okay, the probability that it's greater than 5, you have 6, 7, and 8. Okay, everybody good? The both is the numbers that are even that are greater than 5, so 6 and 8. Okay. All right, so 4 plus 3 is 7, minus 2 is 5 over 8. And that does not reduce, so that's your final answer. 61. A single die is rolled. It says find the odds in favor of rolling a number greater than 2. Okay, so odds in favor equals the probability. Yeah, the probability, no, that's when you're going from odds to probability. So this one, we weren't given the odds. We're looking for the odds. So we want the probability of that event over the probability that you don't get that event, not E. So we want the probability of getting a number greater than 2 over the probability that it's not greater than 2. All right, so how many numbers are greater than 2 on a single die? 4. So you have 4 over 6 over 2 over 6, okay, because 2 are not greater than 2. And so this is the same as 4 over 6 divided by 2 over 6. But that means multiply by the reciprocal. So the 6's cancel. 2 goes into 2 one time and into 4 2 times. And so you have 2 over 1. Now you need to leave your answer in the form of a fraction because you're not going to write it as a fraction. You're going to write it either in words or with the colon in between the numbers. So in my answer key, it has 2 colon 1, okay, the odds in favor, but this is the same as saying 2 to 1. Okay, we're looking at a circle graph or a pie graph. And this is a one-parent household, and this is two-parent household. And it says percentage of U.S. children whose parents are college graduates. Okay, so it says, Part A, what are the odds in favor of a child in a one-parent household having a parent who is a college graduate? Okay, so odds in favor of a child in a one-parent household having a parent who is a college graduate. Okay, so odds in favor is the probability that of E over the probability of not E. That's our formula. So we want a probability of a college grad in a one-parent household over the probability that it's not a grad in a one-parent household. Okay, so this time we have it in percentage, which it's okay to leave it as a percent. So the probability that it is a college grad, according to this first chart here, is 9%. In other words, 9 out of 100. Okay, means the same thing, 9%, 9 out of 100. And so what is the probability that they're not a graduate in a one-parent household? 91%, right. Okay, because it's got to add up to 1 or 100%. If you guys think about that, 100% equals 1. So 91% there. All right, now really what happens is our percent signs cancel out. And so we have 9 over 91, which does not reduce. And so the odds in favor are 9 to 91. Okay, so then part B wants to know the odds against a child in a one-parent household having a parent who's a college grad. Okay, so there's actually no calculations we have to do for this. What is the answer? The reciprocal of that, 91 to 9. Good. So 91 to 9, it's the reciprocal of your answer for the odds in favor. Just flip it over. Okay, one card, this is number 73. One card is randomly selected from a deck of cards. Find the odds against drawing a black king. Okay, so odds against. Well, this time we need the probability that it's not a black king on top, and then in the denominator, the probability of getting a black king. Okay, when it's odds against, just flip that formula over. All right, it might be easier to do the denominator first. So how many black kings are in the deck? No, black kings. 2 out of 52. Okay, only 2 of the kings are black. And if you want, you can reduce that. So 2 goes into 52 how many times? 26. Okay, so 1 over 26. So therefore, what's the probability that it's not a black king? No, well, now that we've reduced it. Okay, so we've reduced. Let's move here. Okay, 25 over 26 is correct. Because remember, that's just 1 minus 1 over 26. Okay, so this means we have 25 over 26 divided by 1 over 26, which really means we're taking the reciprocal and multiplying, so 25 over 26 times 26 over 1. The 26's will cancel, and we have 25 over 1, which means the odds against are 25 to 1. It says the winner of a raffle will receive a 21-foot outboard boat. If 1,000 raffle tickets were sold and you purchased 20 tickets, what are the odds against your winning the boat? Okay, so 1,000 raffle tickets sold. You purchased 20. Okay, what are the odds against your winning the boat? Okay, odds against winning. So again, we're looking for the probability of not winning over the probability of winning. It may be easier to figure out the probability of winning. Okay, let me just write this off to the side here. Well, you have how many chances to win? 20, because you purchased 20 tickets out of a total of 1,000 tickets that are out there. Okay, this reduces, so I know I can cancel out a 0, and 2 goes into 100, 50 times. Okay, so the probability of winning is 1 over 50. And so the probability of not winning is just 1 minus 1 over 50, which is 49 over 50. Good. All right, so this is just going to end up being the numerator times the reciprocal of the denominator. Okay, so I'm hoping we're all there to be able to skip that division step. Numerator times the reciprocal of the denominator. These cancel, and you get 49 over 1, which means the odds against are 49 to 1. Okay, number 87. If you are given odds of 3 to 4 in favor of winning a bet, what is the probability of winning the bet? Okay, so this time you are given the odds, and you want to go backwards now and go back to the probability. So this is where that formula comes into play. The probability of the event equals A over A plus B, where if you have odds in favor, which we do, then this is your A and that's your B. A to B odds. All right, so just substitute in those numbers, and you have 3 over 3 plus 4, which gives you 3 over 7. And so that is the probability of winning the bet. Okay, last question, number 105. On New Year's Eve, the probability of a person driving while intoxicated or having a driving accident is 0.35. If the probability of driving while intoxicated is 0.32, and the probability of having a driving accident is 0.09, find the probability of a person having a driving accident while intoxicated. Okay, in all of the stats that I've written down here, do you see any keywords? Or, yes, very important. Or. Okay, so notice that you see that you have a probability of driving while intoxicated or having a driving accident. And you know what the probability is to drive while intoxicated. You know what the probability is of getting in an accident. So they want to know what's the probability of doing both at the same time. So this goes back to the formula for or, when it's possible that two things can happen at the same time. So remember this probability. The probability of A or B equals the probability of A plus the probability of B minus the probability of both. So notice we have 3 out of these 4 things given to us. So the first thing that they gave us was the A or B. The second thing was the A, and the third thing was the B. What we don't have is the probability of both. Does everybody see how we have those pieces of the puzzle? Okay, so this is the probability of intoxicated or accident, which would equal the probability of being intoxicated, driving while intoxicated, I should say, plus the probability of having an accident minus the probability of both. Okay, that's how we would translate that formula. So now that we've translated the formula, we can fill in the numbers that they've given us. The only difference is this time we know this answer already. We know the or. So the or was 0.35. Just being intoxicated while driving is 0.32. And just having an accident, not intoxicated, just an accident, is 0.09. And so we're looking for the probability of both. All right, we'll go ahead and add these two numbers together, get our like terms together. So 0.32 plus 0.09. So that gives us 0.41. Minus the probability of both. And so we can go ahead and subtract this 0.41 from both sides. So 0.35 minus 0.41 is a negative 0.06, good. And this equals a negative probability of both. So the last thing is we don't want this negative sign here. So divide both sides by -1. And that gives us 0.06 equals the probability of doing both. So, you know, it had a little bit of algebra in there of having to solve for a different variable in an equation. Okay, so this shows you, and this, you know, people that do research on certain things, this is what they're doing. Okay, maybe they were able to isolate what the probability of driving while intoxicated, maybe they were able to isolate these other factors. And so they, you know what would be the probability of both of these things happening? You know, they could isolate that from what they already knew. Okay, so far we've looked at probability. We've looked at how that affects expected value. And then we've also looked at keywords like or, not, and odds. So now we're going to look at the keyword of and. Okay, so two events are independent events if the occurrence of either of them has no effect on the probability of the other. For example, tossing a coin 2 different times. When you toss the coin the first time, that is not going to affect what happens when you toss the coin the second time. So they're completely independent events. Now, this is different than mutually exclusive. Okay, I want to make sure you guys don't get confused with those two terms. Independent events means that you're actually doing 2 completely different activities. Whereas mutually exclusive means you have one activity happening, drawing one card, and can that card be 2 different things at the same time? Okay, so it's mutually exclusive means one event is occurring, and can that event have 2 different characteristics at the same time? Whereas independent events means you have 2 completely different events going on, and they don't affect each other. All right, so a die is rolled, and then a coin is tossed. Find the probability of rolling a number greater than 3, and then the coin landing on heads. So these are independent events, because when you roll the die, that's not going to affect what happens when you toss the coin. Okay? Now, there's 2 ways we can do this. What you have done in the past is you've looked at what all the outcomes were. And a lot of the times the book did this for you, is they listed your sample space. For example, you could roll the die and get a 1, and flip the coin and get heads. Or you can roll the die and get a 1, and flip the coin and get tails. Right? Those 2 different things that you can get. So here are all the different events that could happen. So after you've listed this sample space, then you can find the probability of rolling a number greater than 3, and then the coin landing on heads. So in this list of 12 items, how many times does that happen? Okay, 3 times, I heard. So we've got, okay, so we've got the 4 in heads, 5 in heads, and 6 in heads. So that would be 3 out of a total of 12. And so the probability of greater than 3 and heads is 3 out of 12, which reduces to 1/4. Now, I gave you this list. I could have said, I'm not going to give you the list, and you'd have to generate that list on your own. Okay, a little tedious to come up with that, not super hard, but you have to know what you're looking for. The other way you can do this, if you have a keyword of and, is that you're going to take the probability of the first event and multiply it times the probability of the second event. Okay, so when you see a keyword and, that means you're multiplying probabilities, as opposed to the keyword or, which meant you were adding probabilities. So let's do this problem again, but this time we're not going to list our sample space. We're just going to use this formula. So the probability of the die greater than 3 and the coin landing on heads. So that means all we have to do is find the probability of getting greater than 3 and find the probability of landing on heads. So if you just roll a die, what's the probability that it'll be greater than 3? 3 out of 6. Okay, remember you're giving me a fraction, not just the numerator. So the probability of rolling a number greater than 3 is 3 out of 6. And then the probability of landing on heads is 1/2. Okay, so all we have to do is just get these individual probabilities. Notice that 3, 6 reduces to 1/2. And so I just have to multiply it together, and 1/2 times 1/2 is 1/4. So we got the same answer no matter how we worked it out. This way is shorter, using the formula, than having to list the list of 1 heads, 1 tails, 2 heads, 2 tails, 3 heads, 3 tails, and so on. Okay, because assuming that the problem's not going to give you that list, you'd have to recreate it yourself. So using the formula would be a lot faster. If the probability that South Florida will be hit by a hurricane in any single year is 5/19, what is the probability that South Florida will be hit by a hurricane in 4 consecutive years? Now, that would just be in 1 year. So we're looking at 4 consecutive years. So this is an and problem without using the word and. Okay, because think about what 4 consecutive years means. It means in the first year, and in the second year, and in the third year, and in the fourth year. Okay? So if you have a problem that says consecutive times, or so many times in a row, or something like that, then that is the same as an and problem. So therefore, we're looking for the probability of a hurricane, and a hurricane, and a hurricane, and a hurricane, 4 years in a row. Well, what are we supposed to do with the probabilities when we have an and? Multiply. So we're really looking at find the probability of that hurricane in 1 year times the probability of that hurricane in 1 year times the probability of the hurricane in 1 year, and so on. So the interesting thing about this textbook is I started using it when we got hit by 2 hurricanes in 1 year. And coincidentally, this book had this problem in it. So everybody said, oh, that's a high probability because we got hit 2 years in a row, 2 in 1 year, and so on. Okay, so we're going to take 5/19 and multiply it times itself 4 times. That's basically what you're doing. 5/19 times 5/19 times 5/19 times 5/19. Now, there's another way you can look at this. When you multiply it the same number times itself so many times, what are you really doing? Yeah, raising it to the 4th power, or whatever, however many times you're multiplying it. Okay, so the shortcut, if you need to list this answer as a fraction, then I would do numerator and multiply it, and then denominator and multiply it. So you could do 5 to the 4th, and that'll give you your numerator, and 19 to the 4th will give you your denominator. If you need to list this answer as a decimal, well, then you can put the entire 5/19 into your calculator, especially if you have parentheses, and raise it to the 4th, because then your calculator will give it to you as a decimal. So just keep that in mind, what they're asking for is the answer, what will make it easier to solve it. Okay, so I have the answer written 2 ways here. So as a fraction, we get 625 over 130,321. And as a decimal, it's 0.0047. That's a really small chance that South Florida will get hit by a hurricane 4 years in a row. So again, it looked like it was getting pretty high, but we got hit, 2 years in a row, and then I think the next year South Florida didn't get a hurricane. It came close, but it didn't actually hit South Florida. This one is the one that has the mistake in rounding. It should be 0.0048. What is the probability that South Florida will not be hit by a hurricane in the next 4 years? Okay, what other keyword do you see here? Not. Okay, so we're really looking at the probability of no hurricane. In 1 year, we have to figure that out first. Okay, so the probability of no hurricane in 1 year is 1 minus 5 over 19, which is 14 over 19. So now that we know that, now we can see what the probability of no hurricane and no hurricane and no hurricane and no hurricane gives us. Okay, so taking that 14 over 19 and multiplying it times itself 4 times. Okay, so as a fraction, we get 38,416 over 130,321. And as a decimal, that is rounded correctly, 0.2948. So notice that the probability that South Florida would get hit by a hurricane in 4 consecutive years was only 0.0048. That means that's less than 0.5% that we would get hit by a hurricane in 4 consecutive years. Now, the probability that we would have no hurricane in a single year, in 4 years, meaning no hurricane the first year, no hurricane the second year, none the third, and none the fourth, is 0.2948, which is about 30% chance. So notice that it's much more likely that we would have none in 4 consecutive years than it is that we would have one every single year for 4 years. Now, 30% still is not a high probability. It's still below that 50% range, right? Okay, so then the real question would be, what is the probability that South Florida will be hit by a hurricane at least once in the next 4 years? And that's what a lot of people ask themselves after we got hit by hurricanes so many times in those 2 years. A lot of people moved away because they're like, I don't want to deal with these hurricanes anymore. All right, but really you want to know what's the chance that you'll get at least one in 4 years, and can you live with one in 4 years? Okay. All right, so for this one, you're looking at the keywords at least once. Okay, at least once. That's what you're looking at for this type of problem. And this one's a little bit more complex than the last two. You have seen the words at least once in a previous chapter. Yeah, it was chapter 3. What did we study in chapter 3? Truth tables, okay, logic in general. So chapter 3 was about logic. And you saw the at least once in the word some. Okay, so when we talked about quantified statements in the word some, that was the same as at least once. All right, so the reason I'm bringing it back to that is we know that the probability of something not happening is 1 minus the probability of it happening. Okay, so if you guys remember negations, the negation of some are was none are. Okay, so it went from some to none, if you remember that. Well, negations are sort of like opposites. Okay, the opposite of at least one is really none. So the probability of no hurricane in 4 years is the same as 1 minus the probability of at least one hurricane in 4 years because those are opposites of each other. It's either not going to happen at all or it's going to happen at least once. Okay, those are opposite events. And so that's how this formula actually helps us to figure it out. Okay, so if you rearrange this formula, you get the probability of at least one hurricane in 4 years equals 1 minus the probability of no hurricane in 4 years. Now, I skipped all the work of rearranging it, but that's just algebra, right? You can move this one, add it to both sides, and then you can subtract this one to both sides to get it over to the other side. So all I did was I rearranged it using algebra, and here's what your formula is. So the probability of something happening at least once is 1 minus the probability that it doesn't happen at all. Okay, well, we already know what the probability of it not happening. That's what we just figured out. It was 0.29 something, right? Okay, so all we have to do is say 1 minus 0.2947. Oh, and this is where it wasn't corrected, right? Wasn't it 0.2948? Yeah, okay. Yeah, so it's rounded wrong on this screen. It was, the other one was fine, but this one was wrong. So it should be 0.2948, which equals 0.7052. I think that's right. Yeah, so this final answer was corrected. Okay, so sorry, it was somebody else who came up with this problem, and I tried to fix it. I just did not fix it successfully. Okay, so it should be 1 minus 0.2948, which equals 0.7052. So the probability that we would get hit at least once in 4 years is about 70% chance. those of us that have lived in South Florida for a while, we know, yeah, it's a pretty high probability that we're going to get hit by a hurricane. And you know what? We're okay with that. We've lived through them before, and we'll live through them again. Okay? So that's pretty much the attitude of South Florida for, you know, stereotype there. Okay, now it was just that this was written wrong on the slide. Okay, so it would come out to exactly that answer there. All right, so on your handout, I know I didn't make it really clear on the handout, but on the bottom of the handout there's this little thin box, and it's really for this formula right here. So the probability of an event happening at least once is 1 minus the probability the event doesn't happen. So if you see the keywords at least once, then you're always going to do 1 minus the probability that it doesn't happen at all. So you actually have to find that answer first. That was our second question. You have to find that answer first and then substitute it into this to find your actual answer for at least once. Now, obviously, the time periods have to match. If it's in 4 years, then the other one has to be in 4 years. If it's in 3 years, then they both have to be in 3 years as far as what you're looking for. Okay, 2 events are dependent events if the occurrence of one of them has an effect on the probability of the other. All right, so this is the difference between independent and dependent. So for example, you draw one card, and then you go to draw another card, but you still have the other card in your hand. So if you draw a card and you're keeping it before you draw the second card, what's happened to the deck? It's one less card in that deck. So you have changed what's about to happen. Okay, those are dependent events. Now, if you draw a card and you replace it and you put it back, then those are independent events because you have put that card back and everything's back to normal. So make sure you're listening to keywords like that. Now, if they are dependent events, if the first event affects the second one, then you're still going to be multiplying your probabilities. You've got a probability of A and B, but here's the difference. And I don't really like the word given in there. I keep forgetting to change that in the PowerPoint. It's the probability of A, and then multiply it times the probability of B, assuming that A has occurred. Okay? Change that word given to assuming. I like that word better. So the probability of A times the probability of B, assuming that A has occurred. Okay, so you're dealt 2 cards from a standard 52-card deck. Find the probability of getting 2 aces. Okay, so here's what you're hoping for, 2 aces. Now again, you're dealt 2 cards, so when you get the first one, that's not going back into the deck. You're going to keep it, and then you're going to get the second one. So that's how these are dependent events. All right, so we are finding the probability of an ace times the probability of an ace, and again, change this word to assuming that ace was dealt first. Okay, so when you get the first card, what's the probability of getting an ace that first time? Say that again? 4 out of 52. Okay, there are 4 aces in the deck out of 52 cards. Okay, so there's your first probability. All right, so now you got your first card, and you need to assume that that's an ace. So now what's the probability of getting another ace? 3 out of 51. Good, because not only have the number of aces gone down in the deck, but also the total number of cards have gone down as well. Okay, so 3 out of 51. So this is how that changes. You need to think about what's happened before you write down your next number. Now, you're still multiplying here, so it doesn't really matter if you reduce your fractions. You can if you want. You can also notice that stuff cancels, you know, diagonally and all of that stuff. Okay, now I did go ahead and reduce my fractions next. So 1 over 13 times 1 over 17, which then gives me a final answer of 1 over 221. But it does not matter if you reduce first or if you reduce after you have multiplied. It's up to you. Typically, it's easier to reduce first because then your numbers are smaller. Okay, so any questions on this and? This is another and problem. Notice that the word and was not in there, but it is an and problem because it says find the probability of getting 2 aces. In other words, find a probability of getting an ace the first time and an ace the second time. Okay, so make sure you're keeping track of what an and problem could look like, meaning that you're going to multiply your probabilities together. All right, conditional probability. So you're looking for the conditional probability of B given A. This is why I don't like that word given in the previous problems. The textbook used the word given too many times, I think, and it could confuse you. So you write it like this with this vertical line. So the probability of B given A, the vertical line means the word given, is the probability that event B occurs computed on the assumption that event A occurs. So in other words, it's like getting a hint. It's like, okay, me telling you, you know, I have 6 numbers in a hat, and I pulled out a number and I said, okay, so it's numbers 1 through 6. And I pull out a number and I don't show you and I say, I give you a hint, it's an even number. And you now know some more information about what could be, you know, what could have happened. So that's conditional probability. It's only one event occurring, just one thing's happening, but you're given some more information about what it might be. All right? So, for example, oh, well, let me give you the formula first, sorry. So the formula of the probability of B given A, now, the book gave it to you in set theory first here. Notice that this is from chapter 2. The cardinal number of B intersect A, which is the same as saying the number of outcomes in common to B and A. So how many times can you get both, in other words? Okay, so what the number of outcomes in common to B and A. And then the denominator is the cardinal number of A, or the number of outcomes in A. Notice that the denominator is the same as the second thing listed in your parentheses, if that helps you to remember. It's always your given information, your hint, in other words. So the numerator is what they both have in common. The denominator is only the given part, the second part. You are dealt 1 card from a 52-card deck. Find the probability that you will be dealt a heart, given that the card is red. All right, so in other words, I'm looking at the card before I give it to you, and I said, I'll give you a hint, it's red, and so you have more information about that one card. All right, so you're looking for the probability of a heart given that it's red, which means you want the number of hearts that are red. What do they have in common? Hearts and red, those two things, over the number of red cards. So the denominator is always just the given part, given that it's red, so you need the number of red cards. All right, how many hearts are red? How many hearts are red? 13. There are 13 hearts and they are all red. Okay, so 13 is your numerator. How many of the cards are red? 26. Half the deck is red. So filling in your numbers, you get 13 over 26, which reduces to 1/2. Now notice the difference if you didn't know that that was red. The probability of getting a heart in general is 1/4. Okay, the 13 out of 52, 1/4. But once you know that it's a red card, that probability goes up. And now the probability is 1/2 of getting that heart because you know that it's also red. Okay, what's the probability of a heart given that the card is black? 0 is correct, because notice your numerator would be the number of hearts that are black. Well, none of your hearts are black. That's impossible. And so it's 0 out of 26, but it doesn't really matter. It's 0. It's impossible to get a heart now, given that the information is black. Okay, so here it says you draw 1 card from a 52-card deck. Then the card is replaced in the deck, and the deck is shuffled, and you draw again. Find the probability of drawing a 9 the first time and a heart the second time. Okay, so first of all, what's the key word in this problem? And. So you know that you're going to be multiplying your probabilities. Okay, are these independent or dependent events? Independent is correct. Why? Because the card is replaced. Good. So the card is replaced. So these are independent events. What happens the first time is not going to affect what happens the second time. All right, so it says the probability of drawing a 9 the first time and a heart the second time. So probability of a 9 and a heart, okay, drawing 2 cards. Okay, so we're looking for the probability of a 9 times the probability of a heart. So again, this, and let me just add to it, it's an and problem where there's more than one event. Okay, because you did see the word and in section 11.4 before, but there was only one event. It was just asking you, can it be both at the same time in one event? So here's an and when more than one thing is happening. You're drawing a card twice. So what's the probability of getting a 9? 4 out of 52. And the probability of getting a heart? Okay, 13 out of 52. If you reduce, that's fine because we're multiplying. So some of you guys remember what these were already reduced. So this was 1 over 13 times 1 over 4. So now just multiply them together and you get 1 over 52. Okay, so our probability of getting a 9 the first time and a heart the second time is 1 over 52. Nice work. All right, here's another problem. Elizabeth brought a box of donuts to share. There are 24 donuts in the box, all identical in size, shape, and color. They say that because, in other words, you can't really tell what kind of donut is which. And so 6 are jelly-filled, 5 are lemon-filled, and 13 are custard-filled. You randomly select one donut, eat it, and select another donut. Find the probability of selecting a jelly-filled donut followed by a custard-filled donut. All right, so you're finding a jelly-filled followed by a custard-filled. So you're looking for the probability of a jelly and then a custard. Now, does what you do the first time affect what happens the second time you go for a donut? Yes. Okay, so these are dependent events. And you know this because you select it and you eat it. Okay, you didn't pick it up and put it right back down and not, which you shouldn't do anyway, right? Because then you've touched the food. All right, so you're going to find the probability of a jelly times the probability of a custard, assuming a jelly was eaten. Okay, so what is the probability? And again, here are the numbers. 6 are jelly, 5 are lemon, and 13 are custard. And how many donuts are there total? 24, or 2 dozen. Okay, so what's the probability of selecting a jelly donut? Okay, 6 over 24. And so now what's the probability of selecting a custard now that you have eaten a jelly donut? Okay, 13 custard over what? 23 donuts are now in the box because you have eaten one of them. There were still 13 custard because you ate a jelly. It didn't affect the number of custard that were in there. Okay, but there are now 23 donuts in that box. All right, we can reduce this. Let's see, 6 goes into 24 4 times. 13 doesn't appear to go into anything, right? So multiplying across, we get 13 over 92. Yes, I would agree. Everybody agree with that? Okay. All right, so 13 over 92 is your probability of selecting a jelly, eating it, and then selecting a custard. Any questions and the difference between independent and dependent events? All right, and then let's look at a conditional probability. So that is 13 over 92. Excellent. Okay, so here you have 8 discs that are in a box, and one disc is selected at random. Find the probability of selecting a 7 given that the green disc is selected. Okay, so notice that 1 through 7 is green and number 8 is blue. And just in case, you know, and this happens, okay? If you have trouble seeing colors, it happens. Now, so they've specifically written it under there so that you don't, you know, get confused. There are a lot of people that have, you know, issues seeing colors. All right, so find the probability of selecting a 7 given that a green disc is selected. So what's the key word in this problem? Given. And that's what tells you that it's conditional probability. So you're looking for the probability of a 7 given that a green is selected. So again, it helps to write these out in words. That's what I was trying to encourage you to do in the beginning when we started doing probability. Our numerator is the number of 7s that are green. And then the denominator should be the number of green discs. Good. Okay, so how many 7s are green? Just one. There's only one 7. And then how many of the discs are green? 7. So your probability is 1 over 7. Okay, so conditional probability. The numerator is how many do they have in common of the two things that you're looking at. And then the denominator is always the number that's given, the information that's given. Okay, so 1 over 7. Fantastic. So we get to end on a fantastic.